Hello, everybody. Thank you for joining this joint presentation by the Connecticut Power Electronics Society chapter and the Connecticut APP, MTT, and UFFC chapters. So hello, and for those of you who don't know me, my name is John Noon. I'm a senior electrical engineer at Otis Elevator Company and chair of the Connecticut PELS chapter. On behalf of the PELS chapter, I'd first like to sincerely thank you for joining the webinar presented today by Charlotte Blair and Brian Walker about measurement and simulation of antennas. Before we kick off the webinar, I'd like to give you a short introduction to PELS for those of you who may not be familiar. PELS is a society within the IEEE, which is the largest technical professional society. From what I can see, IEEE is in 5th place behind the National Association of Realtors, the American Bar Association, the American Institute of CPAs, and the American Medical Association, so not too bad of company. PELS's vision statement is to be the global resource that all people turn to for education, knowledge sharing, technical events, and networking in the power electronics field. IEEE PELS core purpose is to foster power electronics technological innovation and excellence for the benefit of humanity. Additionally, so we're also, this is a joint presentation with the IEEE Microwave Theory and Technology Society, IEEE Antennas and Propagation Society, and the Ultrasonic Spheroelectronics and Frequency Societies. So similar to PELS, they're driving forward technology and innovation in their individual kind of niches and areas of electrical engineering. So for both PELS and the previous chapters that I mentioned, so membership, all IEEE membership benefits include online access to the society-sponsored conference proceedings, including, for example, for power electronics, APEC and ECCC, as well as the major journals. Personally, I think it's a huge benefit. So beyond access to technical papers, there are many avenues to get involved, focused on either technical development or more people-focused roles. Both are excellent for professional development, depending on what you want to get out of it. All the different tracks and resources are available on the website for PELS, as well as for the antenna societies. So at the major conferences, so for example, for power electronics at APEC next week, you'd be able to go to different PELS meetings, all the different groups such as technical committees, membership, really everything. They're all looking for volunteers who should be able to align your interests with an opportunity to give back to our profession. To provide some more detail and context on the Connecticut chapter of PELS, we have the same or similar goals as the national organization, but focused on Connecticut engineers. Part of that is through in-person events, but some of that goal is also by broadening our horizons by reaching out into the broader community and engaging nationwide. So you can see a few of the events that we hosted so far last year. So we're a new chapter in the beginning of our second full year of existence. This page shows the events we were the primary host of last year, but we also co-sponsored a couple of additional events with chapters on the East Coast, especially with the Virginia Tech chapter, as well as the Yukon chapter and the Princeton Philly Power Electronics. So stay tuned for our next event in April with the Yale and Yukon formula teams. We're also targeting to connect prospective senior members with current senior members to help them in their IEEE senior member applications. In conclusion, PELS is volunteer driven and about you, the members or soon to be members. So all of our events are open to both IEEE and non-IEEE members, but you know, I do hope you can see some of the benefits of membership. So if you're interested, you can use one of the codes on screen to get a complimentary PELS membership. So as I mentioned, I'm the chair of the Connecticut PELS chapter, but events like this webinar wouldn't be possible without the great support of all of our executive committee members. So if you're interested in getting involved with PELS or a different society, please reach out to me and I'd be more than happy to connect you with the right resources. With that, I'm very happy to introduce you to our speakers today. Brian Walker will present first. So he's the senior RF engineer and subject matter expert at Copper Mountain Technologies. He helps customers resolve technical issues and develops new solutions for VNA applications and test and measurements. Previously, he was the manager of RF design at Bird Electronics, where he directed a team of RF designers and created new and innovative products. Prior to that, he worked for the Motorola Component Products Group and was responsible for the design of ceramic combine filters for communication devices. Brian is the senior member of the IEEE, graduated from the University of New Mexico, has 40 years of RF design experience, and has authored 3 U.S. patents. With that, I'd like to turn it over to you, Brian.
Okay, thank you. Let me see if I can get this rolling. Just a moment. I need to share. Hold on a moment. Now I'm having technical difficulty.
So I stopped sharing, I believe.
Yeah, should be fine. Now I should be able to. Yeah, Zoom has issues with PowerPoint presentations, as far as I can tell. It doesn't allow me to do a full-size presentation. So let me see if I can do. No, it's not going to let me.
I think if you press the presentation mode in the bottom right, it should work.
Presentation mode, bottom right, in Zoom.
Oh, sorry, go back to the PowerPoint, and then if you do the presentation mode from PowerPoint itself, I think we could see your screen briefly there.
Yeah. Okay, so now presentation mode. Oh, this.
Press F5.
Hold on a second. Oh, right there. Yeah. So yeah, the problem with this is it's fine. So
Okay.
am I sharing this? Is it sharing?
Full screen mode.
Okay.
It looks good.
The problem with this is I can't see my notes. So
anyway.
Yeah. Well, that's okay. Hopefully I already know what I'm talking about. I don't need the notes. So let me just minimize the Zoom thing. Okay, so yeah, again, I'm Brian Walker, and my job here mostly is to support our marketing group with technical papers, and I also talk with customers and help them with some of the more stranger problems that customers encounter. So I do have a lot of experience with antennas and cables and all of that. I do have a ham radio license, so been doing that kind of thing for a while. So antennas, a critical piece of radio infrastructure, and no matter how much you pay for the antenna, if the antenna is not optimal, it can degrade the performance of the communication system. So let's see what we can do with a VNA. So some things that you might want to know about your antenna: you got radiation pattern, gain, near and far field distance, impedance, and bandwidth. So this is a radiation pattern for a half wave horizontal dipole. And the only thing I really want to get out of this is that you can clearly see that the radiation pattern is donut shaped, and that along the axis of the antenna there are nulls on both sides. That means, of course, that the radiation is restricted in the nulled area, and so because of that, a dipole is said to have a certain amount of gain. Now, an isotropic antenna, which just radiates spherically in all directions, has 0 gain. So anyway, if there's any possible way that you can direct the energy from the antenna, you're going to create gain. So quarter wave vertical is a little more efficient. The input impedance of this, or the quarter wave vertical, is about 73 ohms real plus a little bit of imaginary. You have to actually, so the actual real part only resonance happens a little bit lower than where it's a halfway length long, so that you end up having to make adjustments to your antenna if you cut it perfectly. So we talk about radiation pattern. There's a lot of different ways to portray it. These patterns, these charts that I'm showing here are typical of what you might see in a data sheet if you're selecting an antenna for your particular use. You can see the bottom right-hand corner, there's a nice 3D representation. I kind of like that, but all these other plots show similar kinds of information. So as I said before, the antenna gain is just all about directing the energy instead of a perfectly spherical propagation pattern or a radiation pattern. If you can restrict it to a certain section, then you're going to have what we call antenna gain. So if you had a 20-degree section, as shown here, then that's 1/18 of the total surface area, and you'd have a gain of 18 or 12.5 dBi. So that's with respect to an isotropic source. Physical antennas, of course, would not have such a sharply delimited broadcast pattern, so and have some radiation in other directions. So you don't never quite get this gain of 18, but you can get kind of close. So we're going to use a VNA. We're going to talk about how we use a VNA to measure antennas. But before we do that, I don't know that everyone is familiar with VNAs, and so I should spend just a moment to talk about how it works and why we might need it. So it's a useful piece of test equipment. I'm sure everyone is familiar with oscilloscopes and spectrum analyzers, and some select few have probably used a vector network analyzer. It is a different piece of gear, and what makes it different is its ability to measure both the forward and reverse traveling waves. Now, you should remember from your 4th grade electromagnetics class that if a media is capable of supporting an electromagnetic wave in one direction, then it is also capable of supporting a reverse traveling wave. Those are the two solutions of the one-dimensional wave equation. So if it can be done, it will. So there will be reflections on almost any electromagnetic media, coax, twisted pair, balanced line, what have you. And the VNA is capable of separating those two signals and measuring them separately. And no other piece of gear is capable of doing that. So how does it do it? The VNA has a bridge inside to separate the incident and reflected signals. And that bridge could be a dual directional coupler, and I'm sure some of the RF engineers are familiar with directional couplers, or it could be a Wheatstone bridge. And that's something that a lot of people are not familiar with. Your common Wheatstone bridge is just a quad of resistors, a diamond shape, if you will, and it's usually balanced such that if you apply a signal across the top two nodes, then anything measured across from side to side will be 0 if all the resistors match. Well, if one of those resistors is just pulled outside and becomes the load of on the end of the cable of VNA, you can see how you can unbalance the bridge. And if you apply 50 ohms, it's balanced. If you apply anything else, it is unbalanced. And so a Wheatstone bridge can be used as a directional detection device. So, and there's an article here in Microwaves and RF. So if we accept that the VNA can separate those signals, what the hell good is it? Well, it generates an incident wave and measures that wave before it leaves the port. A bridge at the port creates the sample signals, then representing that forward and reverse traveling waves so that any reflections which re-enter the port are routed to that reflection port. So we have two samples. Then we have a sample of what's leaving, and we have a sample of what's coming in. We can take the ratio of those, and which is handy because then we don't really care what the power level of the incident signal is. It could vary over frequency, and it does. But if we take the ratio of the reflected signal to what's leaving the VNA, then we have a good indication of what's going on. So because we're looking at that incident signal, we can compare what comes in both in amplitude and phase. So we can represent that reflection which comes back as a complex number, so which has amplitude and phase information. We call that the reflection coefficient. So here's a simple block diagram of our VNA. This is a 2-port VNA, and up top is the stimulus. It switches back and forth between ports 1 and port 2. Port 1 is for, of course, when it's the signal's leaving port 1 and entering perhaps port 2, and it switches over to port 2 so it can do the reverse measurement through your device under test. You can see it has 4 receivers. We call the receivers that measure the outgoing signal, we call those the R receivers. So we have R1 and R2. And the receivers which measure signals entering the ports, we call it A and B for the left and right side. Okay. So let's talk about the S parameters real quickly. So impedance mismatches cause reflections. And you can see here, I've got like a diagram, perhaps it's a piece of glass. There's an incident signal and it's moving through a medium with a permittivity of epsilon 1, and it goes into the glass, which has a permittivity of epsilon 2. And so some signal will go into the glass and some will be reflected. And anything that has a slight change in dielectric will have a different complex impedance. So impedances other than the characteristic impedance of the media cause reflections. And we define that reflection coefficient gamma by the Z that the Z that is encountered, the impedance encountered minus the characteristic impedance divided by the encountered Z plus the characteristic impedance. This is always a number less than 1 with some 1 or less with some phase, which is exactly how we want to characterize our reflection coefficients. So 1 is perhaps total reflection and with some phase, and 0 is no reflection at all. So we calculate these S parameters like this using our receivers, and this is a more complicated depiction of the block diagram of our VNA. We don't actually measure the incident or reflected signals from the bridge directly. We don't digitize those signals because they're quite high in frequency and the digitizer would be very expensive. Those signals go into mixers, and the mixers are driven by an LO, which has a constant offset from the stimulus, which is handy because that gives us a constant IF for each of those receivers. And we can easily digitize that lower frequency IF signal. And the uncalibrated S parameters are just the ratios of these receivers. So we index S parameters based on the source and destination ports. Reflected wave originates at port 1 and returns to port 1, that's S11. And a transmitted wave that originates at port 1, terminates at port 2, we call it S21. So it's S destination source is how we index S parameters. So S parameters are used to quantify voltage waves. I think I'm going to just kind of skip past this because I don't have a whole lot of time. But what good is it to know this reflection? Well, if we measure the forward and reverse voltage waves through our device under test, it gives us a complete model if the device under test is linear. We could save a touchstone S parameter file, which gives all of those reflections in the forward and reverse directions. And we can drop that file into a linear simulator and put different loads on it and different stimuli, and we can see what it will do. So the S parameters in total, if we take them all, give us a perfect representation of the device. So let's get back to antennas. How do you measure the antenna gain? And there are 2 methods. There's the reference antenna method, which is easiest. And then there's the 3 antenna method. Pretty clear, if you have a standard illuminating antenna, that's that orange thing in this picture, We can put a reference antenna on that table across the room, and we can then measure the response as measured by the known gain reference antenna. Then we can do that on our VNA, and then we could normalize that our S21 measurement so that we now see it subtracts from itself, and we now see 0 on the screen. We can then substitute in our antenna under test for that reference antenna. And any difference between the gain of the new antenna versus the reference antenna is the difference in the gain. So it makes it very easy to make that measurement. And we can spin our antenna under test around into different angular positions and get a picture of its radiation pattern. The 3 antenna method. I'm not going to go into this very much, but it is clear that if you make these 3 measurements of actually three unknown antennas, if you like, you can solve the equations and get the gain of all 3 antennas. It does rely on the calculation of the loss through free space, which is this 20 log 10 lambda over 4 pi d. That's from the Freeze equation for path loss. So I think it makes sense. If you make several measurements, 3 measurements, 3 unknowns, you can solve them all. So near and far fields. This is something we need to know about our antennas. If we're going to make measurements, you can't really measure antenna gain if you're in the near field, because close to the antenna, the fields are very similar to static fields. It has radial electric fields and circular magnetic fields that go around the wire or conductor. Those fields don't radiate, and if you think about it, one's kind of oversimplification is to think of a water hose with a stream of water coming out of it. If you jiggle the hose back and forth, you're going to see a kink appear in the stream of water. Well, it's that kink that resonates, essentially, because that electric field is in the proper direction. A radial electric field from the antenna is in the wrong direction for radiation. It has to be perpendicular. It has to be in line with the antenna. So it's that kink which generates the thing which kind of radiates away. Someone once said, shake an electron and light will fall out. That's basically what's going on. But we're interested in the fields that do propagate. So we have to measure far enough away from the near field so we don't get muddied results. And that's called the far field zone. If you want to calculate that, there's a standard method of doing it. You need to be far enough away from the antenna so that, in fact, R needs to be greater than 2d squared over lambda, where d is the maximum dimension of the antenna. For a dipole given here, you can calculate that pretty easily. So what's an open range test look like? Well, if you don't have an anechoic chamber, and I should mention something very quickly before I get to this. If you're making measurements in an anechoic chamber, or even in a far field, perhaps, but let's say in an anechoic chamber, the walls do reflect RF signals to some extent. I mean, it does have those little absorbers, but there's still some reflection in the room. Our VNAs have a thing called time domain gating. So you can actually set up a gate around the antenna under test, a little before it and a little after it, such that you're only going to see signals which occur within that space, which is very handy. So if you're making like reflection measurements or something, and you don't want to see things that are coming off of the walls, or if you're looking at the radiation of the antenna, and you don't want to see what's reflecting off the walls, you can do that. You can gate those reflections out. Gating and time domain functions come standard with almost all of our VNAs. So for an open range, you'd have a far away illuminating antenna. Oh, by the way, how am I doing on time? I think I've got.
You're doing good. Yep.
Okay, good. All right. So if I use a faraway illuminating antenna, as shown here, we can look at our antenna under test and kind of spin it around and see what kind of radiation we get with our antenna under test if we're testing the local antenna. I have kind of a complicated setup here, and there's a reason for that. I have a reference antenna, which is feeding a direct receiver access type of VNA. I'm doing that because I want sort of a reference signal going into the basically the R1 receiver. So it thinks the VNA stimulus is turned off to do this. The signal from the reference antenna is fed into the VNA such that it thinks that that is the incident signal. It's also going into the measurement port. The reason why I'm doing both is because, as you might recall, all of the S parameters are ratioed to either R1 or R2, so I have to have something on R1. So I look at, I feed something into R1 just so that the fraction doesn't go to 0. And mostly what I'm interested in, though, is the reference antenna signals going into the B receiver. So the part 1 is measuring what's coming in to port 1, essentially, from the reference antenna. And then I put the antenna under test, whatever it might be, on port 2. And now I can compare those two very easily by just measuring S21, which gives me the B receiver measurement over R1, or I can measure S. Yeah, so I can do, to get B over A, that is the signal on the antenna under test divided by the reference antenna result. I would measure S21 and S11 and then take that ratio. S21 divided by S11 gives you B over A. And again, R1 has to be a defined signal. All right, so that's how you do a field measurement of an antenna from a faraway source. And then that's nice because the faraway source, you're probably receiving a nice plane wave from it at that point. So when you spin the antenna around, you're not getting the effects of curvature of the RF signal that's illuminating it. So antenna return loss in VISWAR. So one way we want to measure an antenna is perhaps to make the one port measurement. And we can measure the reflection coefficient S11 and the magnitude and phase of the reflection from our antenna that we're driving. So in linear terms, 1 would be a complete reflection and 0 is no reflection at all. And 1 dB on the return loss scale, in dB return loss scale, it's 0 and minus infinity. In VISWAR, that's 1 to 1 and infinity to 1. So of course we want our antenna VISWAR to be as close to 1 to 1 as possible, or we want our return loss to be very low, like minus 15, minus 20 dB would be great. Because if we're exciting the antenna with a stimulus and we measure the reflection and it is very low, very little signal is coming back, well, it kind of has to mean that the signal is exiting the antenna, is being radiated away at those frequencies. It's either that or it's being burned up as the heat. But for the most part, you can test your antenna by just looking at its return loss or its VISWAR. So here's the relationship between VISWAR and return loss. By the way, when we measure S11, the reflection from an antenna, it's usually a negative number, like maybe minus 10, minus 20 dB, tells us that the reflection is a small fraction. But when we say return loss, we usually turn that S11 number into a positive number, just by convention. So if the S11 measurement is minus 20 dB, we would say the return loss is 20 dB. So here's a table relating the two, and you can see that the return loss I have is positive numbers. Why do we care? Well, the voltage standing wave ratio gives the ratio of the peak RF voltage to the minimum RF voltage that we measured if you were to kind of move along the center conductor of the cable. Why is there a standing wave? Well, because whenever you have a signal moving in one direction and the same frequency signal coming back, moving in another direction, it will create minimums and maximums of voltage and current along the transmission line, where those are constructive and destructive. So why is that important? Well, if the maximum tolerable voltage on a transmission line were like a kilovolt peak, and so with a transmit power of 4,900 watts, the nominal peak voltage is 700 volts, which would be great. However, if the VSWR is 2 to 1 on your antenna, it means that you have enough reflection such that you'll be seeing peaks of 1.4 kV, twice the 700, and the transmission line might arc and fail, which is fairly catastrophic for a TV station or a radio station broadcasting 10,000 watts. You also have, you have twice the voltage, but you also have twice the current along the center conductor. And so you're going to get areas with a lot of higher heating, which could cause damage. How might we measure the bandwidth? Well, here I just use a reference marker set at 2 to 1 VSWR on the left-hand side, and I put marker 1 on the right-hand side, also basically at 2 to 1. And I can see that the bandwidth between those two is 141 megahertz. So if I had a specification where my antenna has to be better than 2 to 1 over some range, this is how I would specify it. I would say it's centered at about 2470, 2471, and its bandwidth is 141 megahertz. One last thing, hot antenna measurement. If you're ever measuring an antenna in the field, particularly on something like a water tower, where you have all these antennas at the same vertical height. So there's no vertical separation between transmitting and transmit and receive antennas. It's very dangerous. So if you're evaluating the VSWR or return loss of one of the receive antennas, it's probably picking up a lot of power from the transmit antenna that's off channel. And if there's a sufficient amount of power coming back into the VNA when you're trying to make this measurement, you could damage the bridge. So one way to take care of that is to put a coupler in line. We connect port 2 to the reflection port of that coupler. We drive through the coupler from port 1 with a preamp, a little pad for extra isolation, and we go through the coupler to the antenna. So port 1 is protected from the power of the hot antenna by the pad and the reverse isolation of that preamp. Port 2 is protected from the power by the low coupling factor of the coupler. It might be 20 dB down. So this is how that's done, and it works quite well, actually. Calibration is just done by normalization procedure, and you measure S21, but the result is actually what you would call S11, the reflection from the antenna. What kind of VNA is needed? Well, for most, kind of on-site tests, one port VNA is usually sufficient. There's a, I don't know if you can see my video. This is a one port VNA, USB powered, 6 gigahertz. We have a 14 gigahertz model as well. And it can be directly connected to the antenna cable. And we have a patent for that, actually. This VNA is calibrated at the connector at the factory. So you can do calibration to get a little, user calibration to get a little bit more accuracy. But if you don't need crazy accuracy, the factory cal is plenty good. So you could just take this right out of your pocket and make a measurement on your antenna. For low frequency work, you might look at a 1.3 gigahertz VNA. This is one of those. You could use this to measure your cable, stock end to end. You can make one port measurements with this. It'll run on a 12-volt lithium-ion battery, this particular model here, and it'll go for hours on a pretty reasonable lithium-ion battery. So, questions?
Thank you Thank you very much for the nice presentation. So we have time for a few questions before we turn it over to Charlotte Blair for her presentation on the simulation of antennas, some of the considerations and challenges there. So there's one question in the chat. So Neil Ormos says, could Mr. Walker please explain what a nano VNA is and what capabilities they lack compared to commercial grade VNAs?
Okay. The nano VNA is a great educational toy. You could use it as a ham radio aficionado. You can't beat it. I think it's like $40 or something. You can measure your antennas with those, and it'll do just fine. It has no metrology at all, so you really couldn't use it in any professional capacity. I think though for college classrooms and for hobbyists, it's a go-to VNA for sure. All of our VNAs are traceable, make measurements traceable to NIST. We have on site an ISO 17025 certified calibration laboratory, and we're certified to 50 gigahertz, something like that. There's only like a handful of labs that are certified to such a high frequency. So our VNAs, we can make measurements and we can supply uncertainties to tell you, just how accurate is your measurement, and we can supply that information. The nano VNA is actually not very accurate at all. So, but I can't knock it for its price. It's a great learning, it's a great learning thing.
Okay, thank you. Yeah, it's helpful to kind of understand some of the differences. He has a follow-up question. So one of the VNAs pictured shows connectors labeled 50 ohms. How are systems of different impedance measured?
Great question. We do have a native 75 ohm VNA, called the 7540. It's a 4 gigahertz 75 ohm VNA. So it can make 75 ohm measurements directly and calibrate with a 75 ohm calibration kit. Alternatively, you can actually use a 50 ohm VNA and get a mechanical conversion between this 50 ohm connector and a 75 ohm in or F or whatever you want to use. And then simply calibrate on the other side with a 75 ohm calibration kit. Now you think that might be crazy. You calibrate with a 50 ohm VNA at 75 ohms, what happens? It actually works. All that happens is when you do calibration, you're actually fixing a few things. You're fixing load match on a 2-port VNA. You're fixing load match, source match, directivity, reflection, and transmission losses. So if you calibrate at 75 ohms on a 50 ohm VNA, it's going to just look at it and go, huh, that's a terrible source match. And it's an awful load match, but okay, we'll just correct it. And it does. And so then you can make, after you've calibrated with 75 ohm cal kit, you can make 75 ohm measurements. The only drawback to that is that the correction is fairly severe. The load match is terrible, and the source match is awful as well. Which is okay, but if you calibrate and then through a cable and then move the cable a little bit and change the phase, well, the correction is so large that any changes in phase are going to move your measurement around. So you can do it, you just have to be careful. Alternatively, there is a matching pad that'll take you from 50 to 75 ohms that you just put on the output of the VNA, and that's a better solution.
Okay, that makes sense. Thank you. I have one more question. So kind of in looking at my own work and thinking of the applications that I would use a VNA in the field of power electronics, it would probably be to determine shielding effectiveness and things like that. So rather than aiming to make a very good antenna, it's a very bad antenna. So and some of that goes to the lower frequencies. Like, are there any? I'm kind of curious what the typical like low end frequency range is for a VNA, and if there are any kind of critical things and critical like mindset shifts as you go from like the gigahertz range down to maybe like the hundreds of megahertz range.
Yeah, the shielding effectiveness is important. And I was just looking here real quickly to see if I had something on that. Just one moment. Give me a second. Whoop. Huh. I just had it open, then it died. So what you can do, and let me just share this real quickly. Sure. So if you're looking at something that's supposed to be shielded, you can apply a signal to the thing that's supposed to be shielded, and then you can measure the current or voltage on the shield. And this is one method of doing this. This is called a transfer impedance method, and here a current is applied to the center conductor. And the voltage is actually measured on the shield. So transfer impedance is one way. Shielding effectiveness is another thing you do up to higher frequencies. And here you have this complicated fixture. The reason why it's complicated is because you're trying to measure what's going on the shield, and there really is not supposed to be anything there. So you have to invent you have to have a triaxial fixture, and you have to invent this outer enclosure. So there are ways of measuring shielding effectiveness, and this is basically how it's done. There's a spec for it. Yeah, IEC 62153-4-4. This method is used for that. This is kind of important actually for the cables used in electric vehicles. Those are screened, the big wires, that drive the motors. That's a switched current, and the current is hundreds of amps, and it's switched on and off at a pretty good rate. So those glitches could definitely cause a problem with the electronic driver assist systems and make your car turn left and right or stop. So the shielding effectiveness of those cables is very important to know about. So this fixture is shown here could actually measure one of those cables, and they range from about 1 to 10 ohms in impedance. And that's fine. You just have to do an impedance match at the beginning and a terminating resistor at the end, and then you make your measurement in this fashion.
Okay, well, thank you very much. It's really helpful information.
Certainly.
So with that, thank you very much for the nice presentation. And now I'm going to introduce our second presenter today. Charlotte Blair is a technical support manager for ANSYS. She received her BS in electrical engineering from Rutgers College of Engineering and her MS and PhD in electrical engineering from the New Jersey Institute of Technology. She has supported electromagnetic simulation using industry-known tools for over 15 years. Her real-world experience extends from the design of laser diode transmit modules for Lightel Lockheed to design of filters for wireless communication applications at Cellwave RFS. She's a professional self-motivated team player committed to excellence with hands-on RF, microwave, and laser optic experience, strong field experience, customer service, project management, and communication skills. She's also very involved in the IEEE, serving as the technical co-chair for the 2016 and 17 IEEE Region 1 and 2 Women in Engineering Forum East and as conference chair in 2018. She also serves as the IEEE Connecticut section chair for the Microwave Theory and Techniques Society and the WE chapter, as well as the Region 1 Women in Engineering chair. With that, I'd like to turn it over to you, Charlotte.
Do I need to put on my audio?
No, you should
Okay.
you should be good.
All righty, hopefully everyone can hear me and see my screen. Okay, so let me just add on to a few things that both John and Brian had already discussed today. So thank you again to Otis and for John, who chairs our local Connecticut section for power electronics. And as you said, that I also chair the local Connecticut section for, APS, the Antenna Propagation Society, and MTT-S, which is the Microwave and Techniques and Technology Society, and the Ultrasonics, Ferroelectrics, and Frequency Control Systems. So just to give you a snapshot of IEEE Connecticut, we are 1,300 members strong, okay? We break down our interests in the whole state of Connecticut. The IEEE Connecticut section is the entire state, and our members have told us they are interested not only in computing and processing, but also circuit devices and systems and fields, waves, and electromagnetics. So I encourage you to join us. Look into our activities. If there's a specific activity that you would be interested in, please let us know. Directly connect with John. You could connect with myself or just go to our website. Okay, with that, I just wanted to show in Connecticut, our strongest society here is the Power Electronics Society, so go John. And then we come in with our MTT-S and then APS societies. Okay, so here you just heard Brian talk about measuring antennas with the Copper Valley VNAs. And my day job is with ANSYS. It's an EM simulation company, and I manage the technical support teams. So I'm going to talk a little bit of the challenges that you will see when you're measuring, designing, and simulating an antenna element, okay? And you can see here, I circled or I highlighted IEEE Connecticut system, the tools you need. Well, we need these tools, and here in Connecticut, we can show you some of the things. If I look at, customers across the board, or even if I just did my chat GPT, what are the differences between measurement and simulation? Well, if it's board related, manufacturing process, fabrication tolerances, Brian talked about, and John asked about shielding effectiveness. So the effectiveness of the connector and the cable itself, material properties as they change with frequency, hot antenna measurements. What are your radiation and coupling effects? What are the effects of your environment on your antenna element? And then, of course, calibration standards. We have to make sure that, you do your short, open, and through calibrations on your VNA. So we're here because we know we're electrical engineers and we know what the requirements are from the customer. We could go into any antenna textbook and get equations out and design an antenna. It doesn't matter, what type of antenna. ANSYS does offer an antenna toolkit with their canonical designs, as you can see here. Then we could just put in, we want it at 2.4, gigahertz because we want to do a Bluetooth or a Wi-Fi antenna, and we put the numbers in there, and we put the board information in there, and voila, we get some sort of element out here. And then we can optimize it if we're not at the correct frequency. But as I said, I am not, we don't only do isolated antenna designs. I have a lot of customers calling in, hey, we have this component from this vendor and it's not resonating like they said it would be. What's wrong? Well, our vendors are using not only their product, but there's also an evaluation board, and they design it for their evaluation board. But obviously, our evaluation boards are not what all our customers are using. And it's not in the same environment, because now they have their chip antenna in some sort of package with other things around it, and then they may put it in another package, and they may be using other antennas that may be interfering with the operation, and they want to know why the simulation does not match the measurement. So as we platform and environment does matter when you are doing measurements, and temperature and wind. The one biggest thing that I see a lot of nowadays is our customers, you know, those who are using EM simulation, they're not looking just for single isolated device. They're looking for entire workflows and applications. Now they have this antenna, and now they want to be walking through a room that has test equipment or, you know, outside in the environment. Again, you know, here we go with the temperature. Here we go with wind flow. Here we have not only the freeze equation that we have to look at, but we have to go and think about, you know, what other environmental effects, the heat, okay, different things that, and dielectric properties that will affect your radiation pattern. Okay, so, in short, you know, I'm very conscious of time here. When you go to school, you take your electrical engineering classes, and they teach you circuits, and they give you impedances like, you know, resistors, inductors, and capacitors. And then we go into our EM classes, and, you know, after our basic electrical engineering classes, and then we dig a little bit deeper into impedances, and they're not just magnitude, they're, you know, they're complex numbers, magnitude and a phase with it. And we have to know how they change with different boundary conditions. So different boundary conditions, different air types, different ground types, different air types versus temperature, okay? If there's, again, trees, or if there's walls, or there's metal walls, those are all indicative of boundary conditions. So to boil it down, if you can bring in a geometry of your element as it is where you're going to test it, if you can draw it, then we can simulate it. And when I say simulate it, we're going to simulate it with our EM equations. So with boundary conditions and impedances, we always relate that back to Maxwell's equations. And one of the fundamental equations that we have there, we look at what the relationship between the electric field and the magnetic fields are. And, you know, Brian says, well, there's a difference between near and far. Absolutely, there's a difference between near and far, but we have to be conscious of both of these fields and the impedances that are associated with it. And with that comes the constitutive materials properties, which is the permittivity and the permeability. So that all affects our antenna measurements, and whether they're S parameters or radiation patterns, we need to know what that means. And one of the nice things is, if you can, like I said, if you can draw it, we can simulate it, and we could give you radiation patterns, and we could give you S parameters. But the nice thing about simulation is you could see the differences of an inductor or a capacitor or a resistor on a radiation pattern, because that you can't see. That's invisible to our eyes, right? But how does it matter? I'm going to get out of my PowerPoint because, you know what, I don't want to just talk at it. I want to show you something here. Oops, wrong screen. So this is the user interface. Am I not sharing? Okay, let me see. Go back to here. Okay. Oh, okay. Share. Okay, now let me know if you see it. Good. Okay. So now you can see the front end of our EM simulator, and I happen to be using our HFSS, which is our high frequency system simulator. Yes, it goes down to DC. HF is a misnomer from the past, so it is a full wave EM simulator. Like I said, the one thing that's nice about an EM tool is that you can see the fields. Now here you can see we have components here that are either inductors or capacitors. So there's happens to be two inductors here, and this is a capacitor here. Now, what's nice about the simulation tool is that you can change the value of those, and I'm going to call them parasitic components, right? What are the effects if, you know, if two metals, if a capacitor is in the near field region or the far field region of your antenna element that you're measuring, and or maybe, you know, I have a connector in there and maybe there's an extra length of line, whether it's due for fabrication or just the way it was created. Well, I can go ahead here and I can go in here and see what the effects are on the radiation pattern. So let me just move this back so that you can see it a little bit better. And so I can change it. I did several iterations of the RLs and Cs that are coming in here, and you can see, should be able to see if it's coming through, different values of the capacitor inductor does indeed make a difference on your field patterns. Here I'm just showing the electric field, okay? And you could see that the radiation pattern, whether you're looking at gain and or E field magnitude, it's going to differ. So anything that's nearby that can that you can induce, whether it's wanted or not, a field on it will make a difference. And so if I'm doing this just on a component, this is a chip antenna component from a vendor that allows us to use his their geometry, and you put it on their evaluation board, and you could put it, or your own board, and you can model it, you could see what it's going to affect. You know, you could add a little bit more capacitance, and you could add a little bit more inductance. You know, inductance will change the S11, the resonant frequency of the antenna, but you could actually see why. You know, you could see, oh, am I going to conduct and radiate to a nearby component? All right, so, and this, you won't need HPC on this or as much because these are what we're calling post-processing variables. So, you know, we can change and show you what the trends are, whether if you're going to make a shorter line and reduce the inductance, or if you have a tuning element, or if you have a metallic object closer to your radiating element, maybe you want to increase and or decrease that capacitance and see what the effects are. And again, this is all done in simulation, and it does not take hours or days to run all these types of simulation. Of course, if we were going to include the element and foliage and buildings, and we're going to do space communication, satellite communications, yes, it may take a little bit more time. But there are solvers and techniques that we can do to reduce that time. All right, so getting back to what I would, to the PowerPoint here. Let me go here. How do I get back to my PowerPoint?
I think if you
just go
click
here.
there, yeah.
Okay. All right. And so in the end, like I said, I just wanted to show you that, you know, whether you're working with measurement, whether you're working with simulation, you know, here at IEEE Connecticut, what we can do is we can help you, you know, work the theory. We have lots of great universities here. And then, you know, we have a lot of companies and people who are using our tools. So that is really all I wanted to say. So if there are any questions, I'm open to, you know, anything you'd like to ask.
Well, I have one question to start out with, maybe for both you, Charlotte, and for you, Brian. So listening to both of your presentations, so there's, you know, in the real world, when you're kind of taking a measurement of an antenna, there's certainly a lot of, like as you mentioned, Charlotte, there's nonlinear unexpected results, like you mentioned, fab issues. Yeah, it makes sense, but it's something I hadn't really considered, the maybe nonlinearity of a material property versus frequency. I'm kind of curious to hear both of your perspective and your experience on what workflow you go through. Perhaps, you know, you'll take a design make some rough simulations and then refine and take measurements, and kind of how I'd be curious to hear both of your perspectives on how you go about designing an antenna and kind of your workflows.
I could say something about that. I would also like to say that HFSS or ANSYS is an amazing program. I basically grew up using HFSS and love the program. I guess the important thing to consider is, if you're designing an antenna and it has other materials around it, you need to understand what those materials are going to do to your antenna. Part of that is to understand the material, you might have to measure it and measure its permittivity. There's an article in the current Microwave Journal, March edition, page 66, on materials measurement, which I just wrote. You would use a method like that to measure a plastic enclosure, for instance, to see how that's going to affect your result. And I would actually, knowing the dielectric properties of the plastic, I'd plug that into HFSS and see what it does to the radiation efficiency and the radiation pattern and whatnot. I don't know about nonlinearities. Does HFSS support polynomial or a changing dielectric constant with frequency? I think it does. Okay, so
yes, it does. If you have the measured data, you can bring in that measured data set in there. If you want to use an equation, you can use an equation, and you can even use a parameter, and then you can optimize with a parametric variation. So there are different ways to do that. And as we go higher in frequency, the permittivity, especially if you're using a glass-based board, yes, that does matter. So, we have several different anisotropic materials like FR4, notorious for being nonlinear in the X, Y, and Z. So we do want to take that into consideration. And like you said, we want the radiation, right? So we want a plastic enclosure. What is the distance between the plastic, the air, and the radiating element? That does matter. How does it matter? Well, let's go and simulate it so we can see the fields. And again, the permittivity of, different air, if there's a lot of water content in there, like you said, the hot antennas, maybe the antenna's inside a radome, it's a little bit protected. Its performance may differ if we put that same exact antenna element out in the desert, in the dry sun, and on sand. So it does matter, and when you take those materials of that environment, those properties into account, you may see a difference. And these days, you know what? Every fraction of a dB counts, right? Like before we could take a plus or minus, 20%. Now it's, maybe plus or minus less than 10%.
Yep. Well, I might just add one thing. We've been tossing around impedances and permittivities and permeabilities and whatnot. It's interesting that we talk about impedance, but do we really know what a characteristic impedance means? And so the characteristic impedance is just the ratio of the E field to the H. So it helps you understand the relation, because it's moving through the air or through a media. And you get a certain size E field and a certain size H field at the very same time at right angles. And the ratio between those two magnitudes is the characteristic impedance of the media.
Yep. And that's exactly why, if you notice, I didn't do just gain on my plot. I was looking the real part of E, exactly for that, because, materials matter. Well, what is it touching? I like that murky area that you alluded to. I was laughing at that. That's exactly right.
Yeah, thanks.
Well, thank you very much, Brian. Thank you very much, Charlotte. I really appreciate both of your time and offering your perspectives on this interesting topic. I know I certainly learned a lot. So thank you very much for your time, and thank you everybody who joined the presentation. I'll send out I'll follow up with everybody with a link to the recording of the presentation, so you can check out the good information later and share it with anybody who you think might be interested. So with that, I'd like to thank everybody again and close the meeting.